at Oxford University who's not here today. But everything I'm going to talk about is purely experimental. In fact, there's 0 equations in this talk. I don't know how you feel about that. This is a mathematical institute, I heard. But before I do, I just wanted to briefly mention different types of problems that we like to work on. I like to work with problems that have to do with the dynamics of fluid-fluid interfaces, like a droplet that's entrained in wind. I don't know if you can see. Or this problem right here, talking about studying interfacial instability that's caused by complex morphologies like particles. But I'm not going to talk about any of this. If you like what you're seeing, please, we can talk later. The problem that I'd like to mention today is motivated by studying gas migration in large-scale systems like granular media. We care about this at large because this happens a lot in real life. And of course, these problems are very difficult to study because geologically, this is a very complex system. So the way that we like to take this and study in the lab is by simplifying it. And a lot of people have done this. I'm just kind of reviewing what's already out there. So some people have studied basically injecting gas into a granular water and granular system inside a helical cell. And Rubin's group at MIT did something very similar. Just to wrap this up, though, what we are trying to say, this is a work that's from Sandenes and colleagues, very beautiful paper in Nature Communications, shows that by changing the flow rate, injection flow rate, and the particle volume fraction, you can get a very interesting morphologies. I'm not going to go into this. All is to say that they call this the frictional fluid dynamics. Just to quickly summarize, so in this previous work, what they're mainly doing is to drive gas by basically injection, right? You have a pump that's trying to pump it at a constant rate. And of course, the grains or the particles are resisting this gas migration because of mainly by friction. So that's the whole takeaway message here. So particle motion resists by friction while the gas is just trying to go in by injection. And there's another set of studies that it's been done by Varas and colleagues, very active actually, by looking at the same system that I've mentioned to you before, but by looking at it in a vertical system, so that now the gas is driven or it's being injected from bottom of the cell, and it's basically driven by both buoyancy and injection, while the particle motion is resisted by, again, the friction and the weight of the particles themselves. But where we would like to come in, of course, these are all very beautiful works, and they're doing a lot of studies with this system, is to bring in the element of elasticity. So all the studies that I have mentioned, in some ways, they do have elasticity in that the particles can come together and they can dilate. So there is some macroscopic elasticity, but that's not the dominant feature. So that's what we really like to focus on. And the question is, why is this even relevant, apart from the fact that, of course, we like elasticity. It's very pretty. We actually found some inspiration from the nature itself. So there are people who actually did CT scan of soft sediments and bubble migration in soft sediments. And they found that these soft sediment actually, parts of it act like viscous fluid, like sand layers, whereas the other parts are layers of mud that act more like elastic solid. And the bubbles, I don't know if you can see, it's these dark lines here and these dark circles, depending on where it is, actually act very differently. And based on that, they also did a very simplified study where they're injecting, again, air bubbles into an elastic gelatin here. So here it's now being governed by gravity, friction, cohesion, as well as elasticity. So we just wanted to take this system, even make it a little bit simpler by taking all of those things out. And we wanted to work with a granular media that's really governed by elasticity alone, kind of. So to do that, this is a model system I'm working on. I really have to give credit to Chris, who's been working with these really nice hydrogels for years now. So if you want to purchase these, you should give Chris a call. He really knows where to get them. He doesn't get discounts, but maybe. Okay, so these are, but what's nice is that it's really frictionless. It's very slippery. They don't like to stick together. They're non-cohesive, and they are neutrally buoyant. They actually swell in water, so whatever liquid that it swells in has the same density, and it's very, very soft.
What's the material?
Hydrogel, yeah. So we basically take these nice squishy beads and put them in between glass plates. So we have this nice monolayer of hydrogels that's saturated in water, and we'll be injecting air from top bottom. So that's the nice thing as well. So we're keeping the diameter of the hydrogel to be comparable to the gap thickness, so that we're going to work with a quasi 2D system. So there are a lot of things that we can play with as it is with any simple experiments, but we just wanted to vary one thing right now, which is this height of where we put this permeable spacer. So we call this a permeable spacer because it doesn't quite fit through entire thickness of the gap. So you can see the illustration right here. So that water and air can still rise past it, but it's there to actually confine the particles to a given height. So you could think of H as the level of confinement. And the obvious question we can ask now that we set this nice thing up is to say, for varying H, how does the air migration pattern change? So let's start with a scenario that's very easy to imagine. So in the case where H is far enough away that the particles have enough room to move around, we're going to get the regime where the air is in the fluidization regime, right? So that, oh no, okay, the other direction. Okay. So that just means the mixture pretty much acts like viscous liquid. When you inject air, it's going to rise, form nice bubbles that rise by buoyancy, and then it's going to repeat itself. And of course, towards the top, because of the presence of a spacer, the bubble might linger a little bit, but eventually it gets over it. It goes away. It's nice. And by zooming into a part of the experiment, you can really see that the particles are pretty mobile. They're just basically driven out of the way by rising bubbles. And we will say that, and we're going to say this carefully, qualitatively, this really looks a lot like experiment without any beads in it. Of course, because of the presence of beads, we're modifying the effective viscosity, but overall, we see the same behavior. And to understand the long-term, the overall behavior of these experiments, what we did was to plot basically, so this shade represents the amount of time the air spends in each pixel of the experiment over the entire duration. So this shows you that this is basically the typical trajectory of the air, right, as it goes from the bottom to top from the entire duration of the experiment. So you can see that there's a lingering bubble on the top. That's why there's a darker shade. And of course, if you bring down H while keeping everything else exactly the same, you're going to access another region that's also very familiar. So you can imagine where H is very small, the particles, however elastic and nicely deformable they are, they wouldn't be able to move anymore. There's simply no room. So in that limit, while everything else remains the same, now the air migrates just by pushing the liquid out of the way, while the particles remain rigid. So this is the rigid porous media regime. And by zooming into this experiment, you can really see that the particles do not move at all, which actually makes sense because there's simply no room. And again, the same kind of image processing we did just to illustrate how different the air trajectory looks right now. And you can clearly see these pore spaces or the outlines of particles here, which shows you that air is really getting in between these particles. I just think these are really pretty. So I just really need to highlight this. So the question is, what happens when H is somewhere in between the viscous liquid regime and the rigid porous media regime? And that's where things get interesting, right? Because now the elasticity of particles actually has a chance to shine. So that's exactly what we see here. So this is when H is 12 centimeters. So you see the air coming in, and it's rising, but it's actually acting very differently as it did from the viscous liquid case, because it now has to create a trajectory by pushing the beads apart. So we call this fracturing behavior, and you can really see this in this image right here. When the air comes in, it first has to lodge itself in between the pore space, and then instead of just getting through the pore space, it actually tries to push the particles laterally. So, and I would say that this is not a purely fracturing regime, because we definitely see some pore invasion here happening as well. So if you plot the same image as before, this is what you get. You get this nice almost like a fireworks kind of behavior. And one thing I would mention is that the reason why you see this nice spattering of the trajectory is because we have elastic medium that likes to close itself back up. The fracture doesn't always happen down the same path. That's why you get these multiple pathways. Yes?
I'm sorry, so this is a plot of kind of the density of bubble tracks?
Yes, over the entire time of the experiment.
Do you do particle tracking on the
We do. So it's running right now, actually, just the data is really large. But yeah, because of the setup of the experiment, we are able to identify and track each particle. Yeah. So you can kind of see this all together, and really, these images happen to be very good representation of what's going on. So as you go down in H, we access fluidization, fracturing, and pore invasion, and you can really see how these things change. And this next slide is my favorite of all the slides I've ever put together. So this is with all the experiments that we've done, and you can really see as you go down in H, so the number corresponds to H in millimeters, and how the different regimes are represented in a single plot, which we're very happy with. But apart from plotting pretty things, which is of course nice, we have to measure something as well. So here what we've decided to measure is the amount of air that's present inside the cell at each given time. So there are different things you can measure, of course. You can measure how much air you're putting in, how much air you're putting out or venting at the top. But this is another value that's going to basically give you the idea of how much gas is being trapped at each moment. So what's really interesting is the cases that fall into fluidization and pore invasion, they're right down here. They're not exactly on top of each other, but the order of magnitude is very similar. But something different is happening when you're in this in-between regime, in this green fracturing regime. If you actually zoom in, you can really see the difference. Not only is the order of magnitude or the average volume of air that you trap at each given time different, on average about double, but also its oscillation and the period of oscillation seems to be definitely different from the other two. So we can go ahead and actually plot the average volume of air versus H on a single plot. So this is the fluidization regime, this is the pore invasion, and this is the fracturing regime where you saw the little peak that I showed you before. And turns out this is not a mistake, this is not something that happens only once. You can actually see for a very different values of H, this clear nonlinear behavior of volume of air, or the volume of air that's present inside the cell as a function of H. So I'm just going to try to wrap this up really quick. Oh no, it's so, oh, okay. Can we turn down the lights or something? Okay. Oh, it's so sad you can't really see. Oh, you still can't see. This is really sad. But it's very pretty. You can't see it, but just trust me on this. So I just wanted to thank you, Eric. It's not, okay, I think it's my computer after all. Okay, so I'm just going to try to break down this plot according to the different fluid regimes that I talked about. So the first, for large H regime where the volume of air remains constant, really corresponds to the regime where we had this nice clean air trajectory according to fluidization. This, for small h that falls into pore invasion, we also have very relatively small amount of air that's being trapped. So whatever interesting behavior is going on is right in the middle, where we are actually gradually transitioning from fluidization, fracturing, and pore invasion. And in the interest of time, I just wanted to mention one thing. So one particular interesting behavior that we're observing is that there is this a very sharp increase as you're going from fluidization to what we call fracturing regime in the amount of air that's being trapped. So I'm just going to show you this particular experiment that falls into this orange box, and then we can all eat. So here it is. So this is for H is equal to 13.5 centimeters. So this was the image that I showed you before. So let's watch the video and maybe this will make sense. So you see the bubble rising as it's done before because it's still pretty mobile. But the more air you put in, the more compressed the packing gets. And you find that the air is unable to rise by buoyancy anymore at some point because now the packing is compressing down on the air bubble. So air has to actually grow in size. It just needs help before it can eventually vent out. And although this looks like a one-off time event, that's not true. We can actually measure volume of air versus time for over 10 minutes, pretty much. And you see this behavior repeating over and over again. So what I like to say is that if you are thinking about what are some necessary conditions for you to have this high catcher regime, what you need is to initially be in the fluidization regime so that you get this nice bubble rising. However, you want to be very, very close to the jamming transition so that because of the amount of bubble that you're adding to the system, you actually jam the packing and it can rise anymore. So that's the limit you saw. Oh no, the other way. Okay. So you want to be collecting air bubble, which is very important. And at some point, when there's enough air that's being collected and there's enough packing that's closing down on the bubble to increase the pressure inside the air bubble, you're going to get venting. So I'm going to end this. So this is great. You know, maybe we found something interesting, and at least qualitatively, we're starting to understand this better. So you can just take this idea. So we just found that by varying the amount of confinement, we can change the air behavior drastically. So this is a case, it's clearly unconfined, so you just have a nice air bubble rising. But you can keep going with this. How do I speed up this movie? Is it even playing? Oh yeah, it is. This is very sad because it's very slow, and you guys are hungry, and so am I, and I don't know how to speed it up. But let's be patient. You know, patience is good, I heard, sometimes, in this day and age. Okay, let's go. Okay, bubble rising. So what am I trying to do with this? Aha, we decided that we like this bubble. We don't want it to go anymore. Now we can trap it. So we have a very easy way of suspending bubbles, basically freezing bubbles in space just by changing the level of confinement, which we're kind of excited about. We're not sure if it's useful at all, but we get nice images like this. And with that, we can all go to lunch. Thank you.
Any brave pre-lunch questions? So regarding the elastic fracturing,
Yeah.
it's common. Perhaps the geometry looks sharp and like fracturing, but the physics is very different. Despite I don't think there is a concentration of stress at the front, and maybe you have capillary stresses.
Yeah, I mean, I think you're absolutely right, because if you fracture solid media, you actually have to break the bond, right? So because there's strong cohesion, and we don't have cohesion, we actually just have to break the meniscus between the particles. So you're absolutely right. But I think there is something similar in that when you break the meniscus, you have a choice of you have to push the packing to the side, so you still have to stress the packing as you move it from left to right, basically. So, but you're absolutely right. It is a very different scenario from fracturing like a solid media. Okay.
I'm still hungry, but
Me too.
do you have a sense in the fluidization regime how far the velocity perturbations actually go? Do you still have, even there, kind of tight packing of particles?
So what do you mean viscosity perturbation in what direction?
Maybe it behaves like a viscous medium, but maybe that's kind of local to the bubble because it's kind of stirring things up. But maybe out further, maybe it's kind of creating a channel, and out further it's pretty.
Yeah, actually, that's a really good question. So I think that's where the particle tracking would be helpful. So we don't even know if maybe far out enough the particles over near the walls are not even moving at all. So they're only, maybe it'll be order of the size of the bubble, the the region where the particles are actually rearranging and moving around. That's a really good point. Yeah. But yeah, I don't have a good answer to the question yet. Okay.
We call it a morning and head for lunch. Thank you.